Hello, my name is Marta, and I recently completed my master's thesis project at the Technical University of Denmark. I was working at DTU Nanolab, so National Center for Nanocharacterization, Nanofabrication and Characterization, and the project was done in collaboration with Insight Chips. And the project explored the possibilities and limitations of liquid phase 3D electron diffraction. Today I will introduce you to this technique and highlight some of the applications that might be relevant for research on metal organic frameworks, as the project focused on a specific metal organic framework, ZIF8. And I will jump into and say something about the theoretical background for 3D electron diffraction and liquid phase TEM, as well as I will go through my detailed protocol for the ZIF8 crystallization, in situ crystallization, and what I did with the use of nanotunnel chips from Insight Chips. So let's get started. First of all, liquid phase 3D electron diffraction. The title has two parts. So there's liquid phase and there's 3D electron diffraction. Liquid phase TEM has a lot of advantages. However, it's not that easy to visualize different chemical reactions that are happening in liquid inside the TEM because there's a lot of there's high vacuum inside the microscope. So in order to see reactions happening, which is very cool, we need to use some kind of a liquid cell, so enclose the thin layer of liquid inside membranes that are electron transparent, and that allowed us transmission of electrons through the cell in order to have, and they need also to withstand the pressure difference. So there's high vacuum in the microscope, but our liquid would be in the normal pressure. So we need a specialized liquid cells. However, if we have them, there's tons of possibilities of visualizing, for example, catalysis processes or crystallization or how the crystal structure changes in situ while, for example, changing solvents or flowing in gas to the reactor. And then 3D electron diffraction. It's a technique that is similar to X-ray diffraction, however, uses electrons as a source of irradiation, and it allows us to probe the crystal structure of different materials. It was shown, for example, that um, we can get the crystal structure of a moth, quite specific, different MOFs from 3D electron diffraction data, and it has some advantages over XRD, however, also has some disadvantages. So, my project was kind of a proof of concept. I wanted to show that I can create a reliable protocol for in situ crystallization of ZIF8, so zeolitic framework, zeolitic imidazole framework 8, and that my crystal is single and stable enough and dispersed in liquid in order to collect the 3D ED data on a crystal in liquid. So it will be liquid phase 3D electron diffraction. And then I wanted to collect that data and possibly resolve the structure, crystal structure. So I will go through some theoretical background and then through methodology that I used in the project, and also then go through my results. So, first of crystal structure. Um, all of the materials are, all crystalline materials are built from the small repeating unit. So there is a part of crystal that is quite small but retains the full symmetry and chemical composition of the crystal, and it's called a unit cell. And unit cell repeats itself through all three dimensions of the crystal, building the whole macroscopic structure of the crystal. So if we have a single crystal, it will be built from small unit cells, right? Each one right next to the other. And we choose unit cell based on, in the definition, there's a smallest, word smallest in the beginning. So we choose the unit cell as small as possible. However, it needs to have the full symmetry of the whole crystal and the chemical composition, as I already said. And because it is quite specific for each material, we can compare to different materials, for example, based on their unit cell parameters. Also, from the parameters, we can try to predict what are the macroscopic properties of the crystal or of the material, and then uh, maybe predict how it will act when the different, yeah, with the different stressors. For example, I don't know, maybe pressure or more, or maybe voltage going through it. And then to probe unit cell parameters, we use techniques that are based on diffraction. So we can do that because if we use the irradiation that has the wavelength in the same order, slide like around the same order of magnitude as the distance in between atoms in the unit cell. And for that, we have Bragg's law, which describes how diffraction occurs. And if we have an incident plane wave and it scatters on the periodic structure of the crystal, we can also have later destructive or constructive interference of those scattered waves, and we can see the diffraction pattern. And from that equation, you can see that there's lambda, which is wavelength of our irradiation. There's the scattering angle, which is theta. And then there's d, which is an interplanar spacing in the crystal. And that is something that tells us a lot about how about unit cell parameters. So that's important, and that's what we want to get from the diffraction pattern. And then, as I said, we can diffract, for example, X-rays, as it is already electromagnetic radiation. It's quite easy because those are already waves. And we can use different X-ray sources. So first of all, we can have a tabletop machine with X-ray source, and then the wavelength would be around 1.5 angstroms. And then we can also diffract X-rays produced in the synchrotron sources, and then the wavelength can vary and could be a bit smaller than that. Smaller the wavelength, better the resolution, so we like that. And then there is also a possibility to diffract electrons on a periodic material. Why? Because we can use the electron particle wave duality to describe the electrons. And if we do that, and we assume that the electrons in the TEM are accelerated by 200 kV accelerating voltage, the wavelength of those electron waves would be around 2.5 picometers. So the wavelength is so small that the resolution of the diffraction should be really good. However, unfortunately, we cannot get 2.5 picometer resolution yet, uh, mainly due to lens aberrations in the TEM. So, electron diffraction in 2D and 3D. First of all, electron diffraction is a bit different from X-ray diffraction when it comes to mechanism of interaction. So, because electrons are charged particles, they interact with matter due to strong Coulomb interactions, and those interactions are much stronger than the interactions between the sample and X-rays. And because of that, we can use much smaller samples for our electron diffraction, which is already an advantage because growing a single crystal is not that easy. And therefore, having the possibility to have a smaller crystal, much smaller crystal, is a really good advantage. However, it also means that because the interactions are quite strong, there might occur multiple scattering. So because of that, the electron will scatter more than once on a sample, even though the sample in the TEM is quite thin already. But because there might be a multiple scattering, which is called dynamical scattering, there might be some artifacts, for example, in the diffraction pattern, and it might be a bit harder to analyze it. Because of small wavelength of electron irradiation, the Ewald sphere, so the mathematical tool that we use to describe how the diffraction pattern would look depending on the wavelength of the irradiation, so how many reflections will be on the Ewald sphere. So again, if the Ewald sphere crosses through the reciprocal space, all the reflections that it crosses through from the reciprocal space will be visible in the diffraction pattern. And because Ewald sphere for really, really small wavelengths of electrons will be almost flat, when we zoom in really close to this sphere, the wavelength is so small that the radius is so big that the Ewald sphere is almost flat, which provides us almost an undistorted view of the reciprocal space. So if not dynamical scattering, it would be really easy to analyze the diffraction patterns from electrons, electron diffraction. So how the diffraction looks like, here is the single crystal diffraction pattern taken in the TEM, and here is the polycrystalline sample diffraction pattern. There is a beam stopper because our main beam, so the direct beam, is really strong. So in order to not break the camera, we use the beam stopper in the middle so we cannot see the central point. However, we can see here different reflections. And it's quite easy to analyze them as soon as we know where the central beam is. So the beam stopper, unfortunately, well, does not allow us to get that information from the diffraction pattern. But we can calculate it based on the weights of the intensity around and kind of approximate it. Polycrystalline diffraction pattern looks quite similar to what we see in the powder X-ray diffraction. Well, the idea is quite similar, so we can also see polycrystalline sample rings. And then, what is a 3D electron diffraction? When we have a sample in the microscope, so in the TEM, it's usually based on a holder, and we can tilt the holder with the whole compute stage both ways. So we can have sample, then collect a 2D diffraction pattern, tilt the sample some more, collect another diffraction pattern along different zone axes, and then tilt it again. And that way we would have a sum view of the reciprocal space because we can merge all of those peaks from different tilts, knowing the step size between the tilts. We can visualize the whole reciprocal space as is shown here. However, there is a conical shape in our data that is not there, so there is no data in this part, and it's called the missing wedge problem in 3D electron diffraction. And it means that because there is a limitation of how the holder can tilt, so there's a limitation to the tilt. At some point, the holder would be tilted so high that it would hinder the sample, and also because of the compute stage in the TEM, it's not possible to tilt it 360. Because of that missing wedge problem, we don't have a 100% completeness of our reciprocal space. However, it is still possible to analyze the 3D ED data based on that. So, the project was focusing on ZIF-8, as I said, zeolitic imidazole framework 8, and it's a MOF. Metal organic frameworks are materials that are built from ion clusters, usually the methyl ion, and then some organic linkers. In ZIF-8, it is imidazole, 2-methyl imidazole. And they form such cages, you can say, with the pores inside the structure. Because they are highly porous materials, there is a large surface area of the material, and they are used, for example, in catalysis, or there are applications in sensors, and they can also trap some particles inside the pore sizes, so there could be used in gas storage, for example. And at least ZIF-8, they're quite... So I wanted to say that MOFs are not that hard to synthesize. At least in ZIF-8 case, it is really easy to synthesize, and it creates those pores by itself. So it's quite cool. And ZIF-8 has a few polymorphs. So polymorphs are so it is the same material, it has the same chemical composition. However, the structural arrangement of atoms will be different for different polymorphs. So we can see that, for example, here are two most commonly found in the literature, ZIF-8 polymorphs, and the one here is sodalite-like structure, which has a large pore here in the middle, and it crystallizes in a cubic lattice. Here the pore size is around 3.4 angstroms, and there is also a dia zinc structure that crystallizes in the monoclinic lattice. However, it also has a small pore here in the structure. So the whole project will be focusing on ZIF-8. As I said, it's quite easy to synthesize. However, it's already a porous material that might be of use, and it has a broad range of applications. So it's a bit of a model material that I wanted to use in the project. The only problem is that ZIF8 is a hybrid material, so it's inorganic and organic. And organic materials are susceptible to much higher inelastic scattering effects in the TEM, so so-called beam damage. So under the beam illumination, as considered by a few papers, the crystals of ZIF8 shrink in size. So here, for example, I found a paper that visualizes how crystals look, ZIF8 crystals look in the ambient conditions, so in a dry state, and then as suspended in water and DMF here. And under beam illumination, so the beam is left on, and then different sizes are observed in different time stamps, on different time stamps. And then we can see that the normalized area of ZIF8 crystals is decreasing with time, and the decrease is much quicker in water and EMF than in ambient conditions. So it is most probably due to radiolysis of the solvent, and because under beam illumination, different things might happen in the solvent. So there may be radicals forming, for example, that effects that affect the crystal structure of ZIF8. And then we can also observe it in the diffraction pattern. So here are the diffraction patterns taken of the ZIF8 crystals, and we can see that in time, peaks in the diffraction patterns vanish. And we can see that on the plot of intensity over time. And it can mean that the ZIF8 amorphize during time. So we don't have any sharp diffraction peaks anymore in the spectrum. So it's quite challenging to observe ZIF8 under beam illumination, and for that, some low dose techniques might be used, for example, or it would be nicer to have it in dry state because solvent radiolysis already affects the crystal structure. So all that means that imaging ZIF8 in liquid to use it for 3D in liquid might be challenging, which I knew, but I wanted to explore that anyway. And to do that, I will jump into methodology that I used throughout the project and then tell you about it. So, first of all, my liquid cells that I used for the projects were produced by Insight chips. So, I would say in-house as I was doing my project at DTU. And the chips are made from two silicon nitride amorphous membranes that enclose a really well-defined layer of liquid in a small suspended nanochannels. And the rest of the chip, so here is the imaging window in the middle of the chip, and here is a cross section. So here in the light gray, there is a membrane, another membrane on the other side, and then all the other casing of the chip, so-called, is it's made from silicon, but the electron beam goes through only the imaging window as it's really thin. And the liquid height, so the height of the nanochannels. For this project, I used the nanochannel height around 200 nanometers. However, it can vary from 10, 20 nanometers to I think around 3 microns. So it also might be it might be higher. However, then the resolution will be a bit worse. Silicon nitride thickness in my project was around 25 nanometers, sometimes 20. So the membrane is really, really, really thin. However, it's enough to withstand the pressure difference in between the vacuum in the microscope and the liquid inside. So the chip consists of two bypasses. So there are four inlets/outlets, and each two pairwise are connected by the bypass. So here is a bypass, and here is another one. Two bypasses mean that I can flow two different liquids into the chip at the same time and then observe how they mix in the field of view. And here I will be using that symbol for my presentation. So it is a field of view of the chip, and then top arrow means that I'm flowing liquid through the top bypass, and then bottom arrow means bottom bypass. Of course, I can place the chip however I want, but I was always trying to have the chip that way so I know which one is the top bypass, which one is the bottom. The liquid can be flowed into the chip using a specific holder with tubes inside. but the liquid can be also drop casted onto the chip, and it looks exactly like that. So this is a chip. The inlets and outlets needs to be punctured just before use, and then the liquid can be drop casted, as you can see here, onto one of the inlets, and the liquid will go through the top bypass in this case, and it will fill the whole bypass, which is micron sized, and then creep into the nanochannels because of the yes, because of capillary forces. So, as I said, I will be using arrow on the top for the top bypass and then one on the bottom of the bottom bypass. So, in order to characterize the changes that are happening in the chips, one might also use optical microscopy. So, because there is a window that the viewing window that allows transmission through the chip, it will be also true for visible light. Therefore, the chip can be characterized under optical microscope. So, the chip will have a color because there are different materials and the interfaces between materials and the refractive index of each of them varies. Therefore, the refracted light will show as a color. So, the color of the channels in the chip will depend on three different things. First of all, there's a thickness of silicon nitride membrane, so this thickness here on the top and the bottom. Second one is the refractive index of the medium that is inside the nanochannel. So here, the air or some solvent or crystals, if I want to have crystals inside. So some medium in between, and then the channel height. So, of course, the way that light travels from the top to bottom membrane. Refractive index of air is around 1, and refractive index of water is 1.3. So I will already see quite a bit of a difference between the color if I have an empty channel filled with air or the channel with water. So you can see in the group there were previously the previous member of the group made those color maps, so-called, and they show how the color would look like depending on nitrate thickness and the channel height here. For example, is the air in the channel, and here would be the water. So we know those maps are made knowing the refractive index of air and water, respectively. And then important to note is that the refractive index of ZIF8 is not that different than the one from water, which means that I will not see that high difference between having only water and only ZIF8 crystal inside the channel that is the same thickness, which is a bit of a challenge. So, here I chose another color map just to show you in one of my optical images. So the color map is made for assuming the membrane thickness of 20 nanometers. And then here's the channel height on y-axis and refractive index of solution on the x-axis. So, in the optical image, I could see that some channels are blue, like here, some of them are orange, and there are some other things happening. So first of all, I know that my channel in the chip that I used in this image is around 180 nanometers high. So if the chip was filled with water, it would have a color exactly like that. And then going right with the change of refractive index, I know the refractive index of water is around here. So channels that have this light blue color are most probably filled only with water. Here, for example, or here. And then knowing that my refractive index of ZIF8 is not that different, if the channel height stayed the same, so 180 nanometers, I would have all of the channels in the picture, in the image, exactly the same color, light blue. However, some of them appear orange, and it probably is because there is a crystallization pressure, so there is a crystal growing inside the channel, and because the channel is not really, really high, so 180 nanometers is not that much, then the crystal pushes the channel outwards, creating the higher channel height. And knowing the 1.38 refractive index of ZIF8, I can see that crystals were probably pushing the channel outwards by almost 100 nanometers. There are also some other changes that I can try to analyze. So for example, in that part of the chip, there is also a pressure and the membrane is bulging outwards. However, I can only um, assume that is happening or suggest that it's happening because the resolving power of the optical microscope is not that high. I cannot say for sure what is happening in the chip. However, it's a good suggestion to see how the color of the chip changes and then maybe trying to understand what changes can happen in order to change the color that way. So for TEM data acquisition, I use TECNA 8020. That is here at DTU Nanolab, and the accelerating voltage is around 200 kV. Not around, exactly 200 kV. And here is a picture of TECNA and a lot of tubes and the holder that I used for the project. The diffraction patterns that I took in the project were calibrated and they can be calibrated inside the microscope. However, it's not the case here in TECNA, so I calibrated them manually. And we can do the two ways. So first of all, there is a silicon wedge in the chip that we can collect the diffraction pattern of the silicon wedge, and then knowing the distance from the beam center to the 220 reflection, we can calibrate the pixel size inside the image, so the pixel size here. And it can also be done on the amorphous silicon nitride membrane. So because it's amorphous, it will have a ring pattern. And from previous experiments in the group, we know that the ring radius is around 7.71 over nanometer. So therefore, my diffraction patterns can be calibrated also, knowing that. So liquid phase 3D. I have a chip that I can use for growing crystals in that are dispersed in liquid, and then the chip can be placed into the holder. The holder can be tilted inside the TEM, and diffraction pattern can be collected for each tilt. So that's kind of the workflow, what needs to be done to collect 3D electron diffraction. And there are two problems with the whole methodology. So there is a missing wedge problem, as I already mentioned in the 3D diffraction data. So not the whole reciprocal space would be probed, and also there is a radiolysis of the solvent, which can have an influence on the crystallinity of my sample. So with that, we will jump right into results. So first of all, I did some preparatory experiments last semester because the project was only half a year, so there was not a lot of time to do everything. And as a preparatory experiment, I took the protocol that was existing in the group before and developed earlier, and I tried to see if there's any connection between the concentration of zinc acetate used in the protocol and the amount of crystals growing or the shape of them or anything happening in the chip. So the protocol looked like that. So the arrow means drop casting, as I showed in the video. The solution can be drop casted into the top bypass, and I drop casted it in two inlets just to make sure that the channels are fully, so the whole bypass is fully filled with the 2-methyl imidazole solution, and then that the imidazole solution will be sucked into the nanochannels by capillary forces. So the chip was prepared like that, and as in the video, placed in the holder, and then using the holder, I was flowing zinc acetate solution through the bottom bypass, so by the tubes in the holder, for around 1 to 2 minutes at 300 millibars, using Fluigent flow controller. And depending on the concentration of zinc acetate solution, different things started happening in the chip. But you can see that in both cases, here is 0.04 molar and here is 0.06 molar, sorry. There are crystals growing, appearing in the chip. Here it's not that visible, however, there is a change of color, especially in the part of the chip that has much more dead volume. So because crystallization is a diffusion based process, it needs a bit of space, so the ions need to have a diffusion path and they need to diffuse some. They need to diffuse in order to crystallize. so I can see the crystals appearing in different parts of the chip. However, I would also expect the diffusion to be too small, like the diffusion path to be too small here in the straight channels. As you can see, there are some crystals inside. So there are some things happening that I would not expect. I repeated the protocol under the TEM because, well, of course, I can see some changes in the optical microscope. However, we would not know what is growing inside unless we do an electron diffraction experiment and then analyze the pattern. But unfortunately, my crystals were so beam sensitive that I couldn't collect any diffraction patterns. So you can see that the crystals appear quite like a single crystals, and there's quite a lot of them, at least in that part of the chip. There's also a radiolytic bubble already forming, so the liquid is interacting with the beam. However, unfortunately, I don't have any diffraction patterns, and because of that, I couldn't analyze what crystals are growing in. So going into the other part of the project, I knew that I have a protocol that is kind of working. However, we couldn't analyze the patterns. So I cannot tell you that those are for sure ZIF8 crystals. So for that purpose, I embarked on a journey to try different protocols and see what is working. So, in the group, it's quite common to use rhodamine in water as the first step of creating a protocol. Because, as I said, the chips can be viewed under the optical microscope, we can use the fluorescent filter cubes in order to see mixing of two liquids. So water would not have a fluorescence, but for example, rhodamine solution would have a strong red fluorescence. Therefore, we can see changing the flow parameters and the tube lengths and a lot of different parameters. We can see how it affects the time scale, for example, of mixing. And if we push one liquid a bit more strongly, so using a higher driving pressure, does it change the diffusion happening inside the viewing window? So I tried some experiments based on rhodamine experiments that I did previously. And of course, the diffusion will look differently for not that much differently, but it will be a bit different for each geometry of the chip. So depending on how the nanochannels look, the diffusion process will be a bit different and it could have a different time scale. And based on that, I tried repeating the same experiments that I did with rhodamine, and I saw the mixing with two solutions that do not have any fluorescence, so zinc acetate and 2-methyl imidazole. However, for the rhodamine experiments, we usually use water to fill the chip from two sides, so two bypasses, and then one side of the bypass is exchanged for rhodamine solution. So the chip is fully filled with water first. So the bypass in which I'm flowing rhodamine solution is also filled with water. It cannot be done the same way with the zinc acetate and the imidazole because the crystallization process would happen in the tube where the liquids are mixing and in the bypass, and that would disturb the flow. Therefore, there was an additional step needed, and I poured air through the bypass that in which the zinc acetate was previously. So first of all, I'm flowing zinc acetate in two bypasses, and it's only for filling the whole chip with zinc acetate solution. So I'm sure that there's zinc acetate everywhere. And then air was flowed through the bottom bypass via the holder, and then the air was exchanged for imidazole solution to make sure that um, yeah, I hope that my bypass is clear of zinc acetate, so the imidazole will meet it only in the nanochannels, so in the viewing window. And then I tried tweaking the protocol with different stoppers on the tubes. So here is the SEM holder that I used for optical experiments, which is also produced by Inside Chips. You cannot see the chip inside. However, you can adjust the length of the tubes and you can add some stoppers to control the flow and try doing a lot of different experiments to see which parameters influence the crystallization the most. And unfortunately, for each of those experiments, and I did a few of them, quite a lot of them, honestly, I did not see any visible crystals in the optical microscope. But I remembered that the resolving power is not that strong, so it's not that high. Therefore, there might be something happening, I'm just not seeing it. I also said that before that the refractive index of ZIF8 is not the same, it's not that different from the water one. Therefore, if small crystals were forming, there is a possibility I just didn't see them. Based on rhodamine experiments, I chose the best protocol, and I tried repeating it after failing in optical microscope to see anything. I was trying to repeat it in the under the TEM. And it turned out that there are some crystals inside the chip. However, they were not perfect yet. So you can see there is a bit of agglomerate here from one of my TEM images. And because it was a lot of crystals, so maybe they were single crystals, but agglomerated so quickly that I couldn't collect the diffraction pattern for a single crystal. I tried collecting a pattern for multiple crystals, however, it's really hard to analyze them. Therefore, I didn't really have a way to check if those are for sure my ZIF8 crystals. I found one single crystal. Unfortunately, it was weakly diffracting, so it was a bit sad. And also, you can see that here's the membrane, here's the wall of the nanochannel, and here's the inside of the channel. And the contrast difference in between membrane and the channel is not there, so there is no contrast difference, meaning that the crystal was probably not dispersed in water. I took an EDX spectrum to compare how much zinc I have in those crystalline parts, and then the channel and compared to the membrane. So I used membrane as a background and normalized all spectra to it, and I could see that there is a bit more zinc inside the crystals than than compared to the solution that is inside the nanochannel. However, unfortunately, it didn't look that promising, so I didn't try to improve that protocol again. Maybe it can be done later in the group. So here is just a quick photo to show you how the experiment looks. So here is a holder. There are 4 inlets and outlets. Each of them is connected to a reservoir of water or air or zinc acetate. And then those are some stoppers. And I'm also using the fluid and flow controller. And I need to have 2 units in order to flow 2 different liquids. So it's quite complicated to assemble the whole setup. It takes a bit. Okay, because the protocols with in situ flow did not yield the result I was expecting to, I also tried a bit different approach. So there was a webinar at the Inside Chips page before when Nicolo explained how traps are made, so trap chips, and I also tried to using them for the purpose of my experiments. So the trap chips have a microchannel, so it is a bypass. And then in the nanochannel, that usually is undisturbed and is the same height between 2 bypasses, there is a narrow region. So it's much more narrow than the rest of the nanochannel. And it's called the trap region. Because it's so narrow, usually around 10 nanometers, no particles can go in. It's really hard to make crystals that are smaller than 10 nanometers. So fortunately, we can trap them. But there's another challenge. So in order to use the trap chip, there needs to be an ex situ method of preparation, nano-sized crystals. As a rule of thumb, the crystals should be around half of the height of nanochannel in order to actually go into the nanochannel and not get trapped in the bypass. So it makes it a bit more challenging to make crystals that small. And I wanted to see if that approach could yield in anything, because trapping the crystal here and not crystallizing it in situ might be a much easier way to characterize ZIF8. However, then the synthesis is done in bulk, so it's not really an in situ experiment, and the crystal structure might, of course, differ. So for that purpose, I did a bulk synthesis of ZIF8, and the size of crystals was controlled by the synthesis length, so the reaction time, and also the ratio of concentrations between zinc acetate and 2-methyl imidazole. I have a bright field image of my crystals here. As you can see, they agglomerate a bit, but the sizes of the single crystals are the same as I needed. They are not perfect, but they are good enough to try trapping them in the chip. Here's a histogram of my size of the crystals. And because I used the channel height of 128 nanometers in the trap chip that I used, I knew that I need to have crystals that are below 60 nanometers. And as you can see, I have some crystals that were smaller than that, so I went forward and conducted the experiment. This experiment was done in the Titan E cell at 300 kV, and the beam dose rate was around 1.5 electron per angstrom square per second. Unfortunately, my video is not working. However, I'm sorry about that. Mm, but in the video, so you can see there are some particles that are trapped. So here is the nanochannel, and then this is the trap region. So the trap region is around 10 nanometers. So no particles are visible in that part, but there are some visible in the nanochannel, which is 128 nanometers. And in the video, while the time was passing, there were some more crystals appearing under beam illumination, and after a few seconds, they started disappearing again. So there was a bit of effects that I was not expecting, but they were induced by the beam illumination. And because it was quite challenging to analyze those results, unfortunately, it did not pursue it more. However, it is possible to synthesize ZIF-8 crystals that are small enough to actually trap them into the chips. So maybe if the sample was prepared a bit better or in different solvent, the radiolysis effects would not be that strong, and therefore it would be possible to trap the crystals into the nanochannel and then characterize them fully. So at that point, I decided to go back to the drop casting protocol, so the one that was developed by the group earlier and the one I was having fun with in my preparatory experiments. So I again drop casted the methyl imidazole into top inlets, and then I was assembling the chip. I put the chip into the holder, and then I was flowing the zinc acetate solution into the second bypass. At that point, I changed the concentrations of both solutions based on the best ratio that was also chosen for the synthesis, so 1 to 8, as I wanted to make sure that I'm giving my crystals everything that needs to be done for them to grow as a small crystals inside the nanochannels and hopefully a single crystals. As you can see, there is an optical image here of the chip, and I used straight channels, so the diffusion path was not that long. However, I could still see the crystals, which means that the protocol is quite reliable, and it does not need a lot of dead volume in the chip in order to have proper mixing and crystallization. You can see that there are some changes in the color, and they are more pronounced here, for example, than here. And I tried that protocol a few times and it worked every time. Therefore, that was quite nice. And I also tried preparing the chip like that under optical microscope and then taking it to the TEM. However, the crystals were filling the whole channels and my sample was highly polycrystalline. Therefore, it means that the protocol is really reliable, but it might pose a challenge for creating a single crystal in situ. So the protocol needed to be tested in situ. Unfortunately, it did work. So here's one of my favorite crystals that I obtained using that protocol, but repeating it under the TEM operation. So you can see clearly that here's the membrane, here's the wall of the channel, and here's the inside of the channel. And the contrast suggests that the crystal that looks pretty and has a really pretty facets is actually suspended in water, so in the solvent. And the crystal was single, as I saw in my diffraction pattern, and I was really happy about that. And also in the same chip when I did the final protocol, I found another crystal. It's not that pretty. However, its diffraction pattern was well, I would say model one to analyze. So I reversed the colors. You can clearly see the peaks here, and they are really periodic. And there might be also some effects of having stronger intensity and lower intensity, maybe because of systematic absences, maybe because of dynamical scattering. However, there are some effects visible in the diffraction pattern. But at that point, I can tell you that I have a single crystal that I grew in situ in the chip, and I tried a lot of different ways to do that. So I know which one is actually the most reliable one. However, I'm still not sure if it's ZIF8. So as you remember, I used EDX to see if there is a higher zinc concentration in the crystals, inside the crystals, as compared to other parts of the chip. However, I don't have a definite proof with electron diffraction. And in order to do that, I needed to have crystals that were stable enough, so not vanishing in the beam in the 60-second timescale. So for that purpose, when I found a really nice crystal with a nice diffraction pattern, I collected a few diffraction patterns of the same crystal. So I left the beam on and just let it interact with the sample, and then collected diffraction pattern after 11 seconds, 26, and up to a minute. And then for each diffraction pattern, there was a Python script that I developed, really short one, in which I masked the beam stopper. So that part was kind of cut out of the image. And then from the rest of the image, the script was calculating the radial intensity profile. And then each radial intensity profile was plotted. So they are plotted here on a bit of an offset. And I did it because I wanted to see if the peaks that are quite pronounced also in the radial intensity profile, at least some of them, are moving or if they are vanishing. There is a paper from Jörg Kinschek from DTU Nanolab and his group that discusses the possible mechanism of how ZIF8 amorphize, crystals amorphize, and it suggests that some of the peaks will vanish first and not the others, depending on which lattice plane the pattern was, which reflection was connected to which lattice plane reflection. And some of the peaks can also shift inside the diffraction pattern during the illumination. So I was looking for either vanishing peaks or shifting ones. However, I couldn't see it, which is really good for me. And it was quite interesting. So I can see that the peaks are quite well aligned and the intensity is around the same for each of the timescales. As this experiment was done in Technai, so the beam dose rate is not the lowest, but I knew that I will be using another microscope, that the beam dose rate is much, much lower. 1 minute of stable crystal was sufficiently for me in order to do 3D ED on a crystal. And then finally, how do I know that the crystal is my crystal? So for that, I measured the d-spacing in my 2D image, diffraction image, and the d-spacing can be seen here. It's 1.173, 1 over nanometer, on the calibrated image, of course, diffraction pattern. And then I used CRISPbox software. So it's a software that allows you to load the CIF file, crystal information format file, into the software, and then also upload to the diffraction pattern and see if there's any possible zone axis along which the diffraction pattern might have been acquired that would match one of the zone axes of theoretically predicted diffraction pattern from the CIF file. So it has a structure that I'm suggesting for the software, and then it has an experimental image, and the software checks if there is any match. So the software recognizes peaks in my diffraction image and then predicts theoretically how the diffraction patterns would look for different zone axes from the CIF file. And I checked both my polymorphs that I was expecting of ZIF8 to form inside the channel, and both of them showed a match. However, I wanted to check if software was right, and I plotted the theoretically predicted patterns along the zone axis that the software suggested. And as you can see for the zinc structure, I'm not sure if you can see it, but there's a reflection that says it's 0.61 over nanometer. And then the next one is 1.19. So it showed a match with the second one. However, there is also a reflection in between that I don't see in my pattern. And for the satellite-like structure, there was a first reflection that was seen here was 1.18. Therefore, this structure was a better match. So I can confidently, almost 100% confidently say that I have a crystal that is single, that is stable enough to collect 3D data on it, and that is matching one of the structures I was expecting. So the next step was to take the protocol and then image it into in another microscope. So for that purpose, I used Synergy ED electron diffractometer that is at the electron crystallography facility at DTU and is owned by Casper Pedersen Group. And they helped me with conducting the experiment in their microscope. So for that purpose, I took a holder and I did exactly the same as I did in the TEM at DTU Nanolab. However, this time the microscope had much more functions and it actually allowed quite high tilt range in order to collect enough data, 3D data to and completeness to have a high completeness of data and to resolve the crystal structure. So, as I said, I was not worrying about the beam dose rate anymore because in Rigaku, the beam dose rate for that exact experiment was around 3.5, 10 to minus 3 electrons per angstrom square per second, which is around 3 orders of magnitude lower than the one in Technai. Therefore, the beam damage was not that much of a challenge. And I also saw that the crystal is stable enough for a minute inside the TEM that I was using previously. The tilt range was chosen to be from minus 30 to 30 degrees, and I collected 120 numbers of 120 frames. And in those frames, we found 558 reflections, which half of them were indexed. And the Chrysalis software showed the match with the structure that is surprisingly ZIF-C, which is a structure that was actually resolved by a group in Stockholm using 3D ED data. So it's quite cool. And the structure was with encapsulated BSA inside the ZIF-C. And as I know that in my case there was no BSA anywhere that could be encapsulated, that was quite interesting. However, the structure showed a really good match. And I also wanted to say one more thing, because the beam dose rate was much lower, it was possible to collect the full 3D data in that range that I chose without worrying that the crystal structure might change. However, I put here a snapshot of how the crystal was found. And unfortunately, because the beam dose rate is much lower, the contrast is lower as well. So it made it a bit more challenging to find the crystal inside the chip, even though I expected them to grow in a specific places in the chip already. I couldn't really see them with my own eyes. So for that, we were quite lucky that we actually found this crystal that was strongly diffracting. And we found it, well, by accident, and it was ZIF-C. And also tilt range, minus 30 to 30 degrees. It would be possible to go higher. So Rigaku allows for from minus 60 to 60 degrees. However, with the specific holder from Inside Chips that I was using, it was not possible to go higher as the chip was hindering as the wedge of the silicon from the chip was hindering the sample. However, I know that it will not be a problem anymore as they developed a new holder that will be high tilt, hopefully, quite quickly. So I can show you the result structure from the 3D data. and all the parameters look quite okay. As for electron diffraction, and what is interesting, the structure seems to have not only 2-methyl-imidazole, but CO3 2 minus ions that are connected to the zinc atom here. And it's of course possible because I have zinc acetate as a solution that is flowing in. And also from the paper that I mentioned from group in Stockholm, they postulated that the structure might, so this if it might contain some CO2 built into the structure if the solutions that were used were not degassed. So therefore, I know I didn't do that, and that also might be the case why the structure looks like that. And it's another polymorph, and it crystallizes in an orthorhombic crystal system with the space group PbA2. But it's quite cool because the structure was actually resolved with the help of Mariusz, who is from Casper Pedersen's group, and it is a structure that was resolved from the crystal that was dispersed in liquid, and therefore it is a liquid phase 3D electron diffraction data, which is super cool. And with that, I want to go to conclusions. So I told you something about the reliable protocol for in situ crystallization. There is also a lot of things that I tried and that might work for some other systems that ZIF8, for example, calcium carbonate or some others, but those are a bit, so if you work with some other crystal structure, some other systems, you might be able to use another protocol and it also might work. And we can also observe mixing, not only crystallization, so that's only one of the examples. And unfortunately, the crystal that formed was stable enough to do 3D on it and single, which was also not obvious. So at the beginning, I showed you a lot of polycrystalline samples or agglomerates inside. And then I showed you some 3D data collection and parameters that I used and the result structure. So with that, I really wanted to help everyone that helped me during the project. The project was really short term, so it was not a lot of time. There might be a lot of things that might be done after me. However, I had an immense support from all of those people that I showed here, and of course from Inside Chips with all of the systems that I was using. So the chips, the holders, and some also words of encouragement and experiences that they shared. Thank you very much.